Hey everyone, Patrick Kennedy here with Microchip. In this video, we are going to explore low power modes on PIC microcontrollers that can benefit any battery operated system. If you're interested in embedded systems, robotics, or electronics, and are interested in learning more about these topics, feel free to like, comment, or subscribe. Now, battery operated systems span a variety of fields and industries, ranging from wearables to wireless sensor nodes to robotics. These systems will always have to balance an acceptable amount of weight or space permitted for a power source and the amount of time a device needs to operate while still maintaining an acceptable level of performance. To demonstrate this, we are going to look at an application linked in the description and shown here that uses the Power Debugger and Curiosity Nano platform to analyze the performance and power consumption characteristics of different types of low power modes on PIC microcontrollers. Now, there are three low power modes available for PIC microcontrollers: doze, idle, and sleep mode. As an aside, power consumption in microcontrollers is generally categorized into two components: static power and dynamic power. The main difference between the two is that static power is the power consumed when the system clock is disabled and code is not running, whereas dynamic power is the power consumed by the device when the system clock is active and code is being run. I've included a tech brief resource in the description that provides some more info on this, but the big thing to note here is that both of these topics are crucial for low power design. Okay, so back to the low power modes. Now, if you're anything like me, you probably hit the snooze mode on your alarm clock 3 to 4 times before waking up today. So this is basically how the doze mode works. The CPU will wake up every so often and do something, aka execute an instruction. And the cool thing about this mode is that just like your alarm clock, you as the developer get to decide how long the CPU will doze for in the form of a ratio. For example, 1 to 4, 1 to 8, 1 to 16, etc., etc. In this mode, the system and peripheral clocks will still run at full speed, so all peripherals can still be utilized. This is not so different from idle mode, where the CPU clock is completely halted but the peripheral and system clocks are still functioning at full speed. Idle mode is like doze mode on steroids. Okay, so technically speaking, the idle mode is a special case of the doze mode with a ratio of 1 to infinity, but you get the idea. Now, all of your peripherals will still work in both of these modes, and with the right set of peripherals, and depending on the application of course, this can realistically be the primary mode of operation for the device. Do you need to output a PWM? Maybe you need to change the duty cycle of the PWM. Perhaps you need system comms like I2C and SPI. Maybe you need some logic cell action. Or perhaps you need all of these. With the right set of on-chip peripherals, you can do all these tasks and more with little to no CPU intervention, meaning less code and lower power consumption. You'll notice I said less power consumption, not no power consumption, obviously. Peripherals are circuits, so of course power will be required for them to run. However, the peripheral module disable, or PMD peripheral, allows users to selectively enable or disable any and all peripherals at startup or on the fly, so you can further optimize power this way. Last but not least is sleep mode. Sleep mode completely halts the system clock, effectively turning off the CPU and all peripherals using the system clock. Sleep mode is great for low power, but what if we need to execute background tasks like, high voltage level detect, or perhaps reading a sensor? Fortunately, there are a ton of peripherals that still work in sleep mode. These can include things like an A to D, the windowed watchdog timer, zero cross detect, timer 0, serial communications like the master synchronous serial port, high voltage level detect as I mentioned before, and many, many more. Okay, so let's see these bad boys in action. This project is going to allow us to benchmark the different low power modes by monitoring current consumption as well as the length of time for double EEPROM read and write operations. I've gone ahead and downloaded the MPLAB-X project from the express example linked in the description that includes a tutorial on how you go about setting this up for any device from scratch. I've also gone ahead and configured my hardware as outlined in the express example. Just to reiterate, here is the hardware and software I am personally using when I built this project. Although I am using the PIC18F47Q10 variant of the Curiosity Nano platform, this application should be portable to most newer PIC microcontrollers that have the low power modes available. Just note that you might need to change a couple of lines of code in the application layer depending on the device, which I'll point out later on. Okay, so similar to the linked example, I have my hardware configured as shown to allow the power debugger to function as both a power supply and an ammeter. One important thing to note here is that the target voltage connection, or VTG strap, on the board needs to be cut as well to ensure that we aren't including the power consumption of the debugger in our measurements. Okay, so now that we have all the hardware set up, go ahead and connect both the power debugger and the Curiosity Nano to your computer's USB port. While you're at it, download the express example and open it up in your MPLAB-X IDE like I have here. Open up the Data Visualizer program and connect to the Curiosity Virtual COM port, making sure the settings are the same as mine. It looks like the application is already starting, albeit in active mode. Next, open up the DGI control panel and connect to the Power Debugger gateway, which should open this tab with a variety of interfaces. To enable the Power Debugger to be used as an external power supply, click on the gear icon next to Power and a small configuration window will show up. All we need to do is enable output voltage and drag the slider to the value we desire. So why not just type it into this text box, you say? Because who doesn't want to spend an extra 30 seconds trying to get this just right? Contrary to intuition, this text box is not an input value, and so you'll have to click on the right or left of the slider marker to get your desired output voltage. Hit OK to save the configuration settings. Oh, and I'm also going to disable measurements on channel B just so the graph doesn't look as confusing, but this won't really make or break the application. Okay, so go ahead and hit connect and the power analysis window pops up and we can see the power consumption of the device in its current mode, which is active. I'm getting around 234 microamps. We can follow the instructions on the terminal that will tell us what mode we are in, and the power analysis window will show us the associated power consumption. Let's dive into the code and see how we can set these modes up. Okay, starting with my main.c file, I can see the application task is held in a separate file. Control clicking will take us to the function definition. The main application is held within this application task function that is a switch case statement for each of the modes we enter and exit, plus some miscellaneous in-between states like waiting for a switch press. But all I really want to see is how the low power modes are entered, so let's see if we can find it. Okay, so this activate doze mode function looks promising as it's taking a clock ratio as an input. Let's control click again to see what this function does. Okay, cool, so this is where the doze mode is activated. This function is playing around with some special function registers specific to this device, but every datasheet will have this readily accessible. Okay, so before you close the screen and disgust at the mere mention of registers and datasheets, this register is actually ridiculously easy to work with, so bear with me. So here is the register description from the datasheet. We can see the bits that this function is writing to. Pulling them up side by side, this function only messes with the doze and doze enable bits to enable doze mode and set up the ratio. There is also an ROI bit down here, which just determines if an interrupt service routine will be serviced in full speed mode or in the previously defined doze mode. Control clicking the other functions in the application task function will highlight how each of these modes is entered. I went ahead and consolidated everything we need for basic implementation into this table for more clarity. The bits in red play a vital role in the basic setup to enter and exit each mode. We can see this reflected in the idle mode and sleep mode functions that are called upon from the main application. Going back to the power consumption profile in the data visualizer, we can see how each mode changes power consumption and performance. There are, of course, more advanced techniques we didn't cover to minimize power consumption, such as active clock switching, for example, but we're going to leave that for a future time. Now that you've learned the ins and outs of low power modes, try implementing them in your own projects and sharing them or any other thoughts in the comments below. I've gone ahead and left some links in the description that cover more advanced topics for those who are interested. Also, feel free to like or subscribe if you enjoyed the video. Thanks for watching.